All right, so 7.3, polar coordinates. So the entire semester so far, we've been dealing with rectangular coordinates, which is just the typical Cartesian plane, x comma y, rise over run. So now we want to transition to polar coordinates. So instead of giving a point as a certain width along the x-axis and then a certain height along the y-axis, we're going to give it in terms of a radius and an angle. So you can see it here in this figure. Our angle and our radius are going to uniquely determine x comma y. And so just using right triangles in basic trig, we come up with some relationships between r theta, x and y. So we have a nice little succinct version of that here. So of course we know that x squared plus y squared equals r squared. That comes from cosine squared plus sine squared equals 1. And then we can also compute theta because tan of theta is y over x. We can just compute theta being arctan of y over x. And so we'll use all these relationships to convert between polar and rectangular. So let's do a few examples. So first, starting off in the rectangular system, we're going to move into polar. So for A, you have the point 1, comma 1. So for me, my technique is always to just kind of graph what that looks like. So the point 1, 1 is right here. And because I have an isosceles right triangle, I know that this has to be pi fourths. And also because I have a right triangle, I know that this has to be the square root of 1 squared plus 1 squared, which is the square root of 2. So in rectangular, I'm going to be root 2, which is my radius, and pi fourths. So for B, now we're moving out of quadrant 1. And quadrant 1 is where things are pretty easy when it comes to the conversion. So now I'll have to think a little bit more carefully about what we're going to do. So -3, 4 is, let's say, right here. So this distance is 3. This distance is 4, and I'm creating a right triangle here. So I don't need this angle. I actually need this angle here. This is theta, the whole thing from 0 to wherever I am. So the easy thing to do is compute the hypotenuse. So the hypotenuse is five. So I already know that this is going to become 5 comma something. And just by inspection, I can tell that the answer I get for theta needs to be somewhere between pi halves and pi. Otherwise, I've done it incorrectly. So recall earlier that I'm going to call, actually, give me a second. I'm going to call this little angle in here, I'm going to call him phi. Sometimes expressed like that. So I know that tan phi has to equal 4/3. So from here, I can go to arctan of 4/3 equals phi, and then it's not really like a air quotes easy angle, So I'm going to put it in my calculator. So arctan of 4/3. And I get 0.927. Okay, I can round it there. So make sure you're in radians always. So if phi is 0.927, then theta has to be pi minus phi, which is pi minus 0.9. Which is approximately 2.214. So that is definitely some calculator work right there for you. I didn't round very well. This should be 5. Alrighty, so just to finish, 2.215. All right, and then for our next example, oh, I'm running out of room. 0.3. So for C, this is possibly the easiest one that you could do. So again, just plotting the point, it's right here. So this angle is just pi half straight up, and the radius is 3. So this just becomes 3 comma pi halves. All right, so let's do some where we're going to go from rectangular into, sorry, from polar into rectangular. So for, we'll just skip D. Oh, there's 2 Ds. Ha, in your face, textbook. So we'll go to the second D. So if we're at 3 comma pi thirds, then you still want to be able to graph it. So that's probably something about here. And again, the graph kind of helps with your trig a little bit. For me, it really helps me feel confident in my answer, because once I plot it, I'm like, okay, I know what certain values are supposed to be based on what quadrant I'm in. So here I'm expecting a positive x and a positive y. So I know that this is 3. I know that this is pi thirds. So this is going to give me a 1, 2, root 3 triangle. So I can do that from here. I could also do it algebraically, which let's show that. So we know that x equals r cosine theta. So for us, 3 cosine pi thirds. And so cosine of pi thirds is 1/2, so I get 3/2. And then y equals r sine theta. So I get 3 times sine of pi thirds, which is sine of pi thirds being root 3/2. So this guy becomes 3/2 comma 3 root 3/2. And again, the picture that I drew earlier validates the point that I computed. They're both in quadrant 1. That makes me happy. All right, let's look at E. So I have a 0.2 comma 3 pi over 2. And this is another pretty straightforward one. So 3 pi over 2 is pi and a half. So that's here. And then I'm down 2. So this distance here is 2. So this is just the point 0 comma negative 2. You can absolutely do that by plugging in our x, x is our cosine theta, y is our sine theta, and you will get the same point. I'm just trying to be as efficient as possible. All right, we'll do one more. We'll look at f. So if we have 6 comma negative 5 pi over 6. All right, so this is another kind of a little bit tricky one. So negative pi means we swing out this way. And if I go that way by 5 pi over 6, that means that I have a little baby angle in here. And this guy is pi over 6. Right? So our little phi is pi over 6. So this is our theta. All right. So now what we want to do from here, oh, we need a radius. Hello. So we can let this be our length 6. So I want to know what x and y are. So again, I still have a right triangle, and I could kind of work it out that way. I could also just kind of go blindly. The domain and range, sorry, the domain for sine and cosine are all real numbers, so I could plug in negative 5 over 6, negative 5 pi over 6 and be fine. So I will do that. So I get x equals 6 cosine negative 5 pi over 6, which equals 6 times negative root 3 over 2. So I get negative 3 root 3. So far so good, because I definitely wanted a negative x value. I also want a negative y value. So I get 6 sine negative 5 pi over 6. And that will be negative 1/2 for sine, and so I get negative 3. And so this becomes negative 3 root 3, negative 3. All right, so that is converting points. We've already done a little bit of plotting points here in this example, and I think in hindsight I would have done this example before the other example, but oh well. Yeah, so plotting points in the polar plane is pretty straightforward. My method is just go out to the angle first. And then I extend by the length of my radius. So negative means go backwards, by the way. So for A, I'm at pi fourths, so that's here. And let's say that every one of these lines is just 1. Maybe I'll label that really quick. So this can be 1, 2, 3, 4, 5. Okay, super. So I got to my angle, and then I just want to go up 2. So 1, 2 to the second ring. So this is A. Okay, let's do C, and then we'll do B. So C is 5 pi over 4. So that is here. And my radius is 4. So I go out just 1, 2, 3, 4, the fourth ring. And this is B. And then for the last one, sorry, this is C. Then for B, I'm at 2 pi over 3. So I'm here. And I need to go backwards 3. So what I need to do is I need to follow this line down because I'm not traveling outwards on it. I'm actually going backwards by -3. Notice that it's the same as 5 pi over 3 with radius 3, right? So there's definitely some symmetry going on with polar coordinates. All right. Now the fun stuff. So we can graph a function in polar coordinates, and it's always the same, right? Like make a table, plot your points, nothing's changed. So notice that R is a function of theta, right? So R depends on what theta is. So we're going to have theta comma R of theta. So I make my table for theta, and then I get R of theta based on that, which is 4 sine theta. All right, so we'll just start off at 0, and then we'll do all the quarters. Wow, I did not do a good job on that one. I'm just going to stop actually at, I'll just stop at 3 pi over 2, and you'll see why in a second. So for 4 sine theta, I know I'm going to be 0, and then I get 2 root 2, 4, 2 root 2, 0, and then at 5 pi over 4, I'm going to get -2 root 2. I'm just plugging in the angles into 4 sine theta. And then here I'm going to get 0? No, -4. There we are. So to graph this, so I have 0, 0. Then I have pi fourths, 2 root 2. Okay, so let's actually, how many rings do we have? 1, 2, 3, 4. So if this is 4 and this is 2 and this is 3, then 2 root 2 is like right here. So I'm kind of just going to draw like a little intermediate ring for 2 root 2. Okay, super duper. All right, 0, 0, and then at pi fourths we have 2 root 2. So that's here. But remember that as we're rotating, we're also increasing in length. So you kind of have this like bendy, a little bend to it. Then from here, we go to pi halves 4, which is up here. And again, it's bendy. Okay, and then it should be a little. I'm going to come further around to 3 pi fourths, which puts me back at 2 root 2. So now I'm back down here, but again, more of that bending. Oh, thank goodness, that was awful. At that point, this point. All right, and then, so we've done this one, this one, this one, this one, and then at pi, we come back into 0. So we have this really nice little circle that's just sitting on the origin. If I were to continue with these points, like let's say I was at 5 pi fourths, so remember that example we just did, at 5 pi over 4, I go backwards by 2.2, so I end up right here. So this actually traces itself out 2 times if I let theta go from 0 to 2 pi, which these kinds of things are going to be important in the next section. If I want to trace it out 1 time, I just go from 0 to pi. So there you have it. That is how to graph a polar equation or polar function. And if we wanted to write the equation of this curve in rectangular coordinates, well, it's just a circle centered at 0, 2 with radius 2. So that is just x minus 0 squared plus y minus 2 squared equals 2 squared. Or I could write x squared plus y minus 2 squared equals 4. Okay, I think this is the most fun. To me, this is like a puzzle. So, which I feel like every time I say something is fun, I'm the only one who feels that way. But that's okay. Not everything is as easy as like, oh, hey, that's a circle. I could write an equation for that in rectangular coordinates. Here are some such cases. So if I wanted to rewrite these equations, which are given in polar coordinates, as equations given in rectangular coordinates, I need to still kind of fall back on that conversion we had earlier where x equals r cosine theta and y equals r sine theta and tan theta equals y over x. So I can apply that blindly in the following way. So if theta equals pi over 3, I'm going to use, so I guess in blue, I'll just write my substitution. So I know that tan theta equals y over x. So that would give me that theta equals arctan of y over x. I could use either of those. I'm going to use the first one. They're equivalent, so it all shakes out. I'm going to apply tan to both sides. So tan of theta equals tan of pi thirds, right? Certainly that's true. Tan of theta, though, now I'm using my substitution. This is y over x. So I'll use a little star when I make a substitution, or draw a little arrow. And tan of pi thirds is just a number. So I get y over x equals √3. And then from here, all I have to do is be like, okay, well, y equals √3 times x. This is the equation of a line through the origin. You might think, well, that sounds kind of odd, but think about it in polar coordinates. If you were to graph just theta equals pi thirds, because there's no bound on the radius, this line just extends forever at that pitch. Right? So that's graphing it in polar. here's the equation for it in rectangular. So hopefully that matches up in your mind. All right, the next example, B, we're given that R equals 3. And we know that R squared equals X squared plus Y squared. So I'm just going to square each side. Kind of like in example A, I just applied tangent to both sides. I didn't do any substitution until the third line. Same here. So now that I've squared both sides, I'm going to now make my substitution. X squared plus Y squared, and the right side hasn't changed. Voila, I'm done. So this is just the equation of a circle. And so if you think about the graph of R equals 3, there's no limitations on what the angle can be. So I can be radius 3 here, I could 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 be radius 3 wherever. So that actually forms a circle. All right, and then the last equation, this is the one that's probably, I guess it feels more strictly technical. So I have R equals 6 cosine theta minus 8 sine theta. And I'm just going to write down my substitution. So I don't have any thetas by themselves, so I'm not going to worry about the tangent one. I'm just going to kind of keep in mind that R squared equals X squared plus Y squared, that X equals R cosine theta, and Y equals R sine theta. This also gives me, because I don't have an R cosine theta in here, I just have cosine theta. I'm ignoring the 6 right now. I'm going to rewrite this as X over R equals cosine theta, and Y over R equals sine theta. So I'm actually going to use those in my substitution. So I'm not doing anything on the left, but I am doing some stuff on the right. So instead of cosine theta, I'm going to have X over R. And then instead of sine theta, I'm going to have Y over R. So that was my substitution I made here. And then I want the R's to go away. So I'm going to multiply each side by R. So I get R squared equals 6X minus 8Y. And then look at that, R squared. So I can write that as X squared plus Y squared equals 6X minus 8Y. And then that's it, we're done. And that's the end of the lecture.